Okay, our speaker tonight is Jorge Moreno Soto. He's an associate professor at Pomona College, a professor of physics and astronomy, and he's doing like cutting edge research that he's involved in right now about computer simulation of the formation of galaxies, which I think is something that's really interesting right now because they're being able to look back at those first galaxies with the Webb Space Telescope. So anyway, I give you Dr. Soto.
Thank you for having me tonight. Okay, so talking about time. What are they? Where are they? How do you make them? I guess the real question is why are we even asking this question? It's kind of like asking why do we have cats with suns? Supposed to have a galaxy supposed to have dark matter? So at the beginning, I'll spend a little bit of time talking about what dark matter is or what we think it is and its influence on galaxy formation. You can think of dark matter as the backbones of galaxy formation. What you're looking here is a full sky map of the Milky Way, but the Milky Way hasn't always looked like this. If you go back millions and millions of years, there used to be a lot of really tiny galaxies that merged together through gravity until they made this really big and fantastic galaxy, which we call our home. But before that, I want to acknowledge our home. I want to acknowledge that this is the land of the Tonga Garden, people who still are amongst us. And there are many ways to honor the land. One of them is to really think about where we came from. Think about your father, your mother, your grandparents, and your ancestors. And I think it's really a mystery and also really great that we're here today because of them. Another way to honor the land is to think about the way you treat others, the way you treat your neighbors, the way you treat me, or the way you treat strangers is not just going to affect them right there and then, but it's going to affect 7 generations. It's going to affect their children, grandchildren, and so forth. So as we carry ourselves throughout life, it's really important to hold that responsibility at heart. So this is our home. This is the Milky Way galaxy. Everybody you know is here. Everybody you ever loved or hated is here. All of history and humanity is here. If there is life in other planets and wherever detect that, it's probably going to be in this Milky Way galaxy. And we're not the first to study the Milky Way. Every culture in humanity has done this. For example, this is from South America, this is the Incas. They looked at the southern sky. So in their winter, which is our summer here, around July, in the winter, they see the Milky Way like this. And they say, well, I'm looking at something in the sky and I'm going to interpret it as maybe a llama or a toad, a serpent. So they came up with an idea of the universe. And you might think, well, that's a bit primitive. But if humans come back in 1,000 years, some 2,000 years, and they look at this kind of science we're doing now, they might also say the same. Like, oh, they didn't know better. But I think to get to where we are, we need to explore every possibility. And every culture has done that because curiosity is a human trait that we all share. So this is from the Aborigines in Australia. And what they thought was that the Milky Way was an emu crossing in the sky. If we go to Ghana, West Africa, the idea was, well, I have teenage kids. And so there was a couple who had a teenage daughter who was throwing a tantrum at the fireplace. And she just made a mess, and all those fires went up and created the Milky Way galaxy. This is from Egypt. The god Ra was protecting humanity by covering it with the Milky Way. And in China, well, they think of the universe as a river, and the foam is the star of light that we see today. But I would say the big transition happened with Al-Sufi in Persia, which is today's Iran. I would say Al-Sufi is the father of galaxy evolution, of extragalactic astronomy. Not only did he study the Milky Way, but he was the first person to identify Andromeda and the Magellanic Clouds as independent galaxies. So this is really fascinating because it's after Al-Sufi's discoveries, we started to realize that maybe the Milky Way is not the entire universe. Now, this talk there's going to be a quiz, and also there's a trick, and the trick is the following. I've been telling you all along that this is an all-sky image of the Milky Way. What if I told you that I was lying? This is actually a simulated Milky Way that my collaborators and I created in a supercomputer. Oh, yeah, but because we've gotten really good with the laws of physics and computing that we're able to recreate galaxies that really look like our Milky Way. But the beauty of using supercomputers and simulations is that you can actually run the movie quickly. You can see the evolution, the assembly and evolution of the Milky Way within minutes, rather than trying to wait billions of years. And this is one of the videos that we made with our simulations. So here's the Milky Way. It has a couple of satellites. There's a small satellite that is coming really close to the Milky Way. And what happens is that
What happens? It goes up.
the screen goes up.
Wow.
Well, I was not expecting that.
Yeah, I don't know why.
But the movie's in a loop and we have made for billions of years.
The universe is. There are some things, man.
The universe
Okay, we'll try that again.
That was fun.
It just said, shutting down.
I guess it's a hint.
That might happen to our universe.
Don't say
Let's see if we can,
There you go, Harvey Mudd.
let me, let me, hang on.
Or the slide projector. I can change those things itself.
Display settings.
Monitoring from your app, so in other words, somebody has an action. Raise it up, we roll it down.
Let me see if I can get to Zoom.
You gotta hook up the supercomputer now.
Yes.
Yeah, quantum computing, huh?
I can't even do mine.
So I guess you need to reestablish communications with the outside, Gary?
Yeah, maybe.
I'm sitting in the call.
It says we still have
I'm not.
participants, but I got to tell it that the Zoom is on screen 2 and I want to share screen 2. So that's going to be. Well, air meter, let's see. Well, hang on.
That's a start.
Come on.
There we go.
All right. Enough.
Boy, this is a fast lecture.
There.
The galaxy still lumens.
All right. Sorry about that. The AV system just reset itself.
Okay, so let's look at this again. So this is a simulated way that we created with a supercomputer. And this is how it's coming in and it's getting completely disrupted. And the reason that's happening is because the gravitational field of the Milky Way is destroying it. It's kind of like when a comet is going around the sun, the gravitational field of the sun is disrupting the comet, and that's why it develops it. So galaxies, big and small, they have different histories, they have different stories.
Is the sound on?
Yes, but I have the microphone, which hopefully.
Yeah, I can see the microphone going up and down.
And outside the Milky Way, we have Andromeda, and I saw a nice picture of that with your phone.
Yeah.
Today. So this is a picture of Andromeda, our biggest neighbor. And if you wait 3 to 5 billion years, this is gonna collide with the Milky Way, and it's gonna create a typical galaxy. It's gonna be a real mess. It will be around. Yes, but the nice thing is that we can actually know the motion of the stars in other galaxies because of the Doppler effect. So the Doppler effect has to do with motion and sound. So for example, if you see a police car and you're not moving relatively quick, you're gonna hear the sound. But if that police car is moving towards you, the pitch is gonna go up. And if it's moving away from you, the pitch is gonna go. And the same is true with light. If I'm shining a green laser and I start running towards you close to the speed of light, then the light's gonna get blue. But if I run away from you, the light is gonna get. And that's because light is a wave just like sound. And sometimes I try to use this with a police officer. They said, "Oh, you just run a red light." I'm like, "Well, I was going close to the speed of light and it looked green to me and I couldn't get away from that." So with the Doppler effect, this is what happens. If the meter is moving towards you, light gets bluer. If it's moving away from you, lights get redder. And this is what Vera Rubin did back in the 70s. He's basically taking this galaxy and mapping light. And she thought that one side was shifted to the blue and one side was shifted to the red. This portion is moving towards you, this portion is moving away from you, and that tells you this, the direction of the rotation of the Milky Way. But here's the thing, if you take the axis of rotation and you look at places away from that axis of rotation, you can see that the chunks of galaxy are moving at different speeds. And that tells you something about the mass content of the galaxy. So if you take all the light from the galaxy and you measure its luminosity, you can get a sense of how many stars you have, how much mass in stars you have. And then if you use the laws of physics, then you can get a prediction of how quickly the galaxy should be rotating as a function of distance from the center. And this is what she predicted. Well, it should rise up and then it should go down. It rises up because as you move away from the center, you have more and more stars. But eventually it peters out because gravity gets weaker the farther away you are. Like the gravitational pull from the sun is weaker than that of the moon because the moon is closer, even though the sun is more mass. Now, this is what you would expect from Newtonian physics, but this is what the observations tell us. That things are actually moving faster than they're supposed to. And this was really intriguing. It's kind of like these things are moving so fast that the galaxy should just shred itself apart. But for some reason, it's staying together. And the reason we believe that's happening is because of dark matter. So Vera Rubin and others said, well, there is this extra substance that we don't know what it is, but that's the thing that's holding the stars together in the galaxy, so they can spin quickly without flying away. It's kind of like if you're washing your clothes and you see your clothes are spinning, there is something that's holding them together. It will be the washing machine. In this case, the dark matter halo is the thing that's gluing everything together. We don't know what dark matter is. We know how much there is, and we know what it's not. So we know it's not planets, it's not compact objects, but it might be either, what I believe it's probably really tiny particles just flying everywhere. And hopefully with particle accelerators, we'll be able to see them directly one day. But as of now, we just know that the dark matter has to be there, that it has an effect on the motions of celestial objects. And I like to think of ghosts when I think about dark matter. When my son wakes up, he's like, oh, somebody folded my clothes, somebody made my breakfast. There must be a ghost doing all these things. And I'm like, no, your father is doing all of that. But just because you don't see it, doesn't mean that I don't exist, but you see the effects of me doing that, just like we see the effects of dark matter on the motions of stars around us. So this is a computer simulation of dark matter. Of course, dark matter doesn't glow in visible light, but in a computer, we can pretend that it is. So the brighter regions are the more dense regions, and this is in the very early universe. So in the very early universe, you had a lot of really tiny halos, and because of gravity, they merged with each other until eventually they made one giant halo pulsing the Milky Way galaxy. You notice that this kind of looks like neurons or like this web structure. We call this a cosmic web. And the densest regions, the regions with the most mass, they start attracting matter from the outskirts. So it's a bit like capitalism. The richer get richer. Here, the more massive systems get more massive. And hopefully you start seeing that a central structure is being made in the center. And that's where the galaxy will be. But I'm not including the stars and the gas that we can actually observe. I'm only showing you the dark matter. And you see that the distribution is not really smooth. Like when people say a dark matter halo, you imagine this really smooth distribution. You see, it's very clumpy, and there are tons and tons of those objects. So when you look at galaxies, it turns out that the amount of dark matter they have depends on the mass of the galaxy. So something like the Milky Way has some large stellar mass, and as you go into smaller and smaller galaxies, the mass in stars goes down. But if you look at the dark matter halos, it turns out that the mass in dark matter also decreases, and we know this by looking at the rotations of stars in these galaxies, but it doesn't decrease as fast. If I take the ratio of stars to dark matter, that fraction actually increases. The tinier the galaxy, the more dark matter it has. So I'm spending my sabbatical at Carrick observatories simulating these tiny galaxies because they have a lot of dark matter. And the way to think about this is, well, why would a tiny galaxy have such a chunky halo of dark matter, whereas something like the Milky Way doesn't have that much? How many of you like coffee?
Yeah.
So the way I think about this is, imagine I have espresso cup and I have an Americano, and I put them in the microwave for 2 minutes. Which of the two is going to make a mess first? The espresso, right? So the same is happening here. If you have a tiny halo and you have stars, those stars, they live their life, they explode as supernovae, and because the halo is so small, the energy from the supernovae blows out the gas, and then most of the gas doesn't turn into stars. So the process of galaxy formation, the process of turning gas into stars is very inefficient because you have this small halo that cannot hold things together, just like the espresso model. Whereas for something like the Milky Way, you can have a lot of star formation, you have a lot of supernovae, but because you have so much gravity, the halo is not going to let that stuff escape, and then you end up with a more massive galaxy. So hopefully I can convince you that when you're looking at tiny galaxies or dwarf galaxies, those are supposed to have the most dark matter. This is what the simulations predict, and this is what the observations tell us. But there is an exception. So here this is a visualization from the Hubble Space Telescope. We're zooming into a group called NGC 1052. This is 60 million light years away. And there are some galaxies here and there, but we're zooming into a dwarf galaxy. This galaxy is very diffuse. If the lights were on, we wouldn't be able to see it. So this is a really intriguing galaxy. This is called NGC 1052, DF2. So what about this galaxy? So I'm just going to call it DF2 for short. What you can do is you can take the light from all the stars in the galaxy, add it up, and it tells you more or less how much mass you have. And this galaxy has about 1 billion solar masses. Billion sounds like a lot, but this is like 50 times lower than the Milky Way. So this is a low mass galaxy. We would expect the galaxy to have a higher fraction of dark matter than the Milky Way, right? Because of the arguments I gave you before. So my colleagues went and used the Keck telescope, and they used the Hubble Space Telescope to look at these star nuggets that we call globular clusters. So these galaxies have collections of really dense collections of stars within 1,000 and 1 million stars orbiting the galaxy. And if you look at the motions of those globular clusters, that can tell you how much dark matter you have, right? If these globular clusters are moving slowly, you probably don't have a lot of dark matter. But if they're moving very quickly, that tells you that there has to be a lot of dark matter holding the galaxy together. So this is what they found. They found that if you use the motions of these globular clusters, they found that the total mass of the galaxy is also 1 billion solar mass. So here you have 1 billion in stars, here you have 1 billion in total. So what is the mass in dark matter? The difference, which is 0. The galaxies are weird because there is no room for dark matter. All the matter is accounted for in stars. And this is really a challenge to the last 50 years of research, where people have said not only that galaxies should have dark matter, but that tiny galaxies have even more dark matter. This is a tiny galaxy with apparently low dark matter. So when people discovered this, everybody freaked out. Observers started fighting, like maybe your measurements are wrong, maybe your velocities are wrong, maybe the distance to the galaxy is actually closer, so it looks brighter than it actually is, and maybe it should have a lower mass. There's been a lot of fighting. I've been invited to give talks at other continents so people can challenge me about the discovery. And then I tell them, I'm actually not in that paper. I'm doing simulations to explain that, but I'm not in that paper. You don't need to fight me. But if you want to fight me, then fly me to Europe and I'm happy to come. So anyway, so this galaxy, after this was in 2018, and in 2019, they found another one. This is called DF4. I'm just going to call them DF20. And these are really weird. Now, observers were fighting about this, and then people could do simulations like me. We're starting to race to try to make simulations explain them. And every group around the world tried. They all failed except us. I'm really proud of this. These two galaxies are actually neighbors. They live in the same group. So just like I told you, like the Milky Way has satellites, this massive galaxy has satellites too, and two of them are these two dark matter free galaxies. So what is going on? So there's been a lot of theoretical scenarios. The first one was from 1998. This was before the galaxies were discovered. This person, Priya Natarajan, and colleagues, they came up with an idea. Maybe there is a way to make galaxies without dark matter, and someone should look for that. And what she said was, well, if galaxies have supermassive black holes in them. So supermassive black holes are black holes are objects that are so dense that light cannot escape. For example, if I throw a ball here, it's gonna come back, right? But if I throw it at 11 kilometers per second, it's gonna escape. So there's escape velocity that Earth has. If I went to Jupiter, that velocity would be like 200 kilometers per second. With black holes, it's the speed of light. So there's nothing you can do. If you throw something, if you're in a black hole and you throw something up, even light is gonna come back down. So these things are dark and they're really massive. But if there is gas around them, when gas starts falling into the black hole and orbiting the black hole, there is a lot of friction, right? And what happens when there is friction? There is heat, there is power, there is light. So what's happening is, as the gas is trying to fall into the black hole, the gas is really hot, it emits a lot of light, and we call that a quasar. So what these people are saying is, well, when you have a quasar, when you have all this light coming from the regions near black holes, that light is gonna push the gas, and it's gonna push it up, and eventually that gas is gonna collapse into space. It's kind of like if I'm boiling water, the steam from the water goes to the ceiling, and then it turns into water. In this case, the gas from the quasar is coming up outside the halo, and then it cools down and collapses into stuff. So that's more or less the idea. And I think it's a bit of a wild idea, but we said, well, we can test that in our simulations. So this is a simulation of a galaxy, and each time is zooming in, and you notice that it's the smaller the region, the faster things are moving, right? And all the action is happening here. This is the center of the galaxy, that's the supermassive black hole. And because there is so much energy coming from the gas falling into the black hole, it clears out this region because all this power is pushing things. And we call this a quasar. Now, can a quasar make a galaxy? Well, we followed a bunch of gas, these green particles or gas in near the galaxy. What happened is the quasar is blowing out a lot of energy, and it's actually compressing the gas that's falling in. And you see those stars that are popping up, it's basically gas turning into stars. You're making new stars because this quasar is compressing the gas and forcing the gas to turn into stars. So you might say that this is a galaxy, but this object is actually in the center of the galaxy. It never leaves the galaxy. So Natarajan and those others, they say, oh, a quasar is going to be able to compress the gas really far away from the galaxy. Our simulation shows that there isn't enough energy to do that. And you can make stellar objects, but they happen to be inside it. So with our simulations, we show that that idea, although interesting, is not really viable. The second scenario was, well, maybe you saw that the group had like these satellites and there was this massive galaxy in the center. Maybe interactions between the tiny galaxies and the massive one can actually do something about this. This is a paper we published in Astronomy a couple of years ago, and it's gotten a lot of attention, good and bad attention. I still get angry emails about this paper, but I think this is the way it happened. So let me tell you more about this. So what we did is we ran a simulation of a big chunk of the universe. So each of the here is a galaxy. And I'm showing you the gas, and this has been really hard to do. Like I remember doing simulations 10, 15 years ago. I didn't even imagine we would have the computational power or the physics understanding to actually be able to pull this off. And you see, just like the movie I showed with dark matter before, galaxies also follow this web-like pattern. In a way, galaxies are like cities. There are places that have a lot of galaxies, and there are places that are really empty. Because like it's not the same growing up in Los Angeles or Sao Paulo versus growing up in Iowa, which is in the field. With this simulation, we were able to find 7 galaxies without dark matter. And we were kind of curious. I was curious about their names. Like, what should I name them? I told my collaborators, well, I found 7. What do we do? We live in Southern California, so they were like, oh, well, how about the Disney characters? I was like, oh, that's kind of goofy. And also, it's like, I imagine, like, if I were a person with dwarfism and I saw this paper and I was like, these dudes are making fun of me. So I said, like, no, that's not really cool. That's not good. Then someone said, what about the 7 sisters in mythology? I was like, yeah, I'm not Greek. I'm not a woman. I didn't feel like it was my place. I'm a person of indigenous ancestry. I have Kickapoo roots. I have ritual roots. So I asked myself, well, maybe in the indigenous tribes, in native lands, they have the number 7 might be relevant. I have a friend who's Cherokee. He lives in Dallas, Fort Worth. And he told me, you know, I'm Cherokee, and in the Cherokee tribe, we have 7 clans. And each clan has its own history, its own cuisine, its own culture. And these are matriarchies. So the heritage goes through the mother. And the names are wolf, wild potato, pink, blue, long hair, bird, and deer. So I asked my friend, hey, can you ask the elders of the tribe if they give me permission to use the names? Because I want to be respectful, because I'm not Cherokee. And he communicated with them, and they were like, yeah, sure. So that's what we are calling the 7 galaxies, after the 7 Cherokee. And each of them has its own history and its own personality. And get ready, because the quiz is coming. So this is the first one. This is Wolf. This is more like a Milky Way galaxy, but this Wolf is right outside. So it's that little nugget in that circle. That's Wolf. This is the stellar light from the galaxy. And I want to remind you that this is a simulated galaxy. This is not a real galaxy. This galaxy lives in a supercomputer. But we can calculate how much light you get per you can get how much blue light you get, how much orange light you get. And the idea is to try to make it mimic what you would see with the Hubble space. So sometimes I tell people, hey, what's the name of this galaxy? And they start coming up with names. I'm like, no, this is a simulated galaxy. This is a virtual. And the nice thing about simulated galaxies is that in addition to being able to see light, we can also see where the dark matter is. So this is the map of the dark matter. So this center of this galaxy has a lot of dark matter, but Wolf is actually free of dark matter. It doesn't have its own halo. This is wild potato. Again, it's close to a big galaxy, and it doesn't have a halo. And paint, it is a fluff. I like this one because it's kind of fluffy, kind of chubby. And this guy doesn't have a halo. So here's the quiz, but you're allowed to talk to each other. What do these 3 galaxies have in common? So talk to the people next to you or behind you, and let's see what they come up with. Let's take a couple of minutes. And if you're shy like me, you just get out of your comfort zone and make friends. Go. There are no wrong answers, so don't be shy.
I think they're all a little elliptical, but weird elliptical. Yeah.
Looks like the center. It's what they call them. They look like comets. They're similar. But they don't have the same shape. No.
I see.
What?
Yeah.
Okay, so-
I know.
Oh, yeah, okay.
So this energy, yeah, let's see, then it starts to show. Right away.
There's one more minute.
Well, it could be another 20 minutes.
Also, what's his, piece of the
Any other
circles
things you see?
or somewhat similar.
Yeah, to me that yeah, like they were talking, they look like comets, you know, that and
Yeah.
so is one circling, you know, or are they rotating around each other, you know, or
They're probably being disrupted by the big.
yeah, I don't know.
All right, do you need more time?
Do you grade on the curve?
I'll just take the group average.
No, I don't know.
All right, let's get started. So what did your neighbors tell you?
What did you tell me?
Where are you paying attention to them? Well, what did you tell your neighbor?
So she pointed out that in front, but she pointed out that it looks asymmetric and the tails going, it's like, and I said that looks like tails. And so, you know, maybe it looks like it's been, you know, like a comet going close to the sun.
So they have tails. So you have like a nugget and you have tails.
Yes.
And the tails are in the direction of the bigger galaxy.
Right.
So you're saying that maybe the bigger galaxy is disrupting,
Yes.
just like a comet. I think many people were saying that.
Yeah.
What else?
Close enough to undergo some gravitational disruption with bigger galaxy, like its a merger starting.
So they seem to be very close to a massive galaxy, right? And that's so these effects can be effective. What else?
There's a lot of haze around those galaxies.
A lot of haze, probably stars that are being stripped.
Yeah.
Well, yes.
The tails, well, to me, it's like a lighthouse, it has tails on both sides.
Yeah,
And
like
they all end up going toward the center of the galaxy in a way.
and with a comet, you would expect a tail on one side, right? But here it's like it happens on both sides because the tail is catching up with the galaxy is catching up with its own tail. So this thing is holding around me. What else? I want you to look at the star color of the big galaxy and the smaller galaxy. So the big galaxy has a lot of blue light, while this tiny one don't. And blue light tells me something about recent star formation. So blue stars, they only live like 100,000 years, whereas red or orange, yellowish stars, they live millions of years, even billions of years. So if you only have reddish stars, it means that the galaxy is really old. Whereas if you have a lot of blue stars, it means that star formation is still ongoing. So in the massive galaxies, there's a lot of blue lights because there is still gas around to make these.
So would that be earlier one than the other one? The other one would be older?
So the other ones are older, they stopped making stars a long time ago,
Okay.
whereas the massive ones are still making, like the Milky Way, are still making stuff. It's kind of like if you go to a village and it has dogs, humans, and turtles. If it still has dogs, it means that the village is at most 15, 20 years old, right? But if it only has turtles, it means that the village is at least 150 years. Because it only has turtles. So the press, depending on what you have in the village, tells you something about the age of the village. They kind of starts instead of like you get from galaxy, tells you something about the age of the galaxy. Those things are reddish and really old. There is another obvious thing they have in common. What is this talk about? So these don't have dark matter. And the last one is I want you to look at the massive galaxy, especially these two, especially this guy. This one looks like the eye of Sauron, right? And this one, you can see it's still, you can barely see it here, but you see that we have a disk, and then the inner disk is kind of dislodged. You have a main disk, and then you have an inner disk that is kind of like twisted. Who do you think is the culprit of that?
No, the galaxy.
That little guy. If you go back in time, you can see the trajectory of that tiny galaxy, and it actually crashes inside the bigger galaxy and it messes that. So those are some of the things that can give you clues about their formation. But I told you there were 7 of them. I've only shown you 3. So what about the other 4? This is long hair. Long hair is really far away from the center of the halo. And has a really weird orbit. This thing came in, it crashed with the galaxy, it went to the other side, it left the main galaxy's dark matter halo, so it was free for a while, and now it's on its way back. And this is a lot like DF2 and DF4. You saw that elliptical galaxy with those far away satellites. This guy is really far away. And if you were to observe it, you would say, well, maybe that this galaxy and the massive galaxy in center they haven't interacted. But in simulation, you know that because you can run the movie back. And this is the dark matter distribution. It doesn't have dark matter. And the last 3 are bird, blue, and deer. Deer is kind of fluffy. And it's also a galaxy that came in, left the halo, and it's on its way back. So it has crossed twice. Blue and bird are a couple. They worked together before joining this halo. They were dancing, and then they fell in, and now they're part of this group. And if you look at dark matter distribution, they don't have dark matter. I'm not a very visual person, and I'm sure many of you as amateur astronomers are very visual people too. And the first thing I do when I run a new simulation is look at images. And just by looking at images, I get a lot of clues about what's going on. And I start making hypotheses, and then I go back and analyze them. So it seems like there is a interaction between galaxies is the driver of making galaxies without dark matter. You start with tiny galaxies with a lot of dark matter. They crash with the central galaxy multiple times, and in that process, they lose their dark matter. I also find that in order to make dark matter efficient galaxies, the ratio of stars between the two has to be about 1 to 1,000. If these galaxies are too similar, they're going to merge before you're able to make a dark matter efficient galaxy. And if these galaxies are very different, the little one is going to disrupt before you're able to make a dark matter efficient galaxy. But there is a sweet spot of 1 to 1,000 where you can actually create dark matter efficient galaxies. And the condition is that you have to come within 5% of the dark matter halo of the host. So you have a massive galaxy, it has a dark matter halo, you measure the radius, you take 5% of that. If a satellite comes within 5% of that, we find that that satellite becomes a galaxy lacking. So those are the 2 conditions we predict. That extreme galactic collisions generate galaxies without dark matter. And I just want to know, just coming back to the names, as an indigenous person is really important to me to acknowledge, for example, my own history of someone who has native roots but speaks European languages, has a European name, wears European clothes. These galaxies too, they had their own identity, they had the dark matter, but in this process with colliding with the bigger galaxy, they lost that identity. And this is really important to really think about this and to think about where we come from and all the diversity we have in as a people. Elections are coming up, and there is a lot of divisiveness, and I invite you to try to see the commonality between people. Just like these galaxies are very similar to each other, people you run into in the streets, people who you might disagree a lot with, they have more in common with us than between. And one of the things we have in common is love for the universe and love for our origins. Thank you for your generous attention. And what questions do you have?
Yes.
We were talking about galaxies that have their dark matter strip. Would the mechanism be in the dark matter of one galaxy interacting with the dark matter of the other galaxy? Or is there some other, or does it react at all with normal matter?
So stripping of dark matter, we've known about it for many years, and it's usually the standard picture how we know it's dark matter with dark matter. But this collision is also extreme that actually the dark matter of this tiny galaxy is actually also colliding with the regular matter of the bigger galaxy.
Because it does interact regularly.
Yes, and it's very dramatic because this is really dense.
And as a follow-up to that, we have galaxies, some of the smaller ones that have their dark matter strip from. Is there any evidence showing concentrations of dark matter that are not associated with galaxies or baryonic matter.
Oh, so if you saw the movie at the beginning that there were a lot of superhalos, people are looking for those. And so in fact, for many years, the tension had been there are too many dark superhalos and not enough satellites. This is a bit of the opposite. But people are looking for these dark superhalos. And one way to do that is you saw that these galaxies have these streams, right? So what some of my collaborators are doing is they're looking for interactions between those streams and these dark superhalos. So you have a galaxy has a stellar stream, and then a superhalo passes through and pierces through the stream. So people are looking
And you
for
can
those.
see the effect.
Yes, so I think if they pull it off, they will get the Nobel Prize, but it's really hard. Mhm.
I imagine so, but people are looking for it. That's
Yes.
neat.
Yes. Any other questions?
So your dark matter hypothesis is, your intuition of non-baryonic, particles?
That is my intuition, although some of my colleagues are also, they've been coming up with an idea called fuzzy dark matter. And the idea is, if you look at an electron or a photon or quantum particles, they behave both like particles and waves. So they say that this is a quantum particle whose wave properties are out of the scale of galaxies.
Okay.
So that's another idea. And some of my friends are running simulations with that model. I think it's really wild, but also really interesting.
Very large.
Yeah, like a wave function that is
The
size of a galaxy. Yeah.
If dark matter has a gravitational effect on normal matter and also with itself,
Mhm.
how concentrated could isolated dark matter become? Could it ever get to a point where it could, for example, cause lensing from light behind it or something like that?
Yes, and that's something that also people are looking with the JWC. They're looking for the gravitational lenses of dark particles. But the story has often been like, hey, I found this lens and it doesn't have a galaxy in it. And then people follow up with massive telescopes on Earth and then they find out few tiny stars. But it's one of the papers I'm writing is on the ability of a halo to make a galaxy. And I'm finding some dark halos that have a little bit of gas, but they don't make stars. So those might be around. And you could observe by looking at for the gas without finding this.
Yeah, probably what may seem to be a stupid question, but these objects, if you have found seven of them, you have what I guess you might call a visible light depiction, and then you have another one that shows dark matter depiction. The first row that you have there, it shows the dark matter in visible light. Is that just basically a computer thing that enables you to just show where this dark matter is? It's not something that you would actually see in a telescope, right?
Exactly.
Okay.
So the
that's what I
top
was
one,
wondering.
so the computer tells you what the stellar mass is,
Okay.
and then you can use a lot of physics to tell you how much stellar light you get.
Okay.
And it also tells you what the dark matter mass is, but there is no lot of physics that tells you how it should glow because dark matter
Yeah.
is dark.
That's what was confusing to me because by definition, I guess dark matter is dark.
Mhm.
So you just don't see it.
Yeah, and we know where it is, so we assigned it a color in our maps, but in reality, we were trying to make a realistic image, it would be completely dark.
Okay, yes, okay, that makes sense.
And the only way to know where it is, I'd say things like lensing or how it affects emotions on stars.
If dark matter is dark and it doesn't interact with photons or anything like that, it means it also doesn't block them in any way. So you can't see, okay, here's a clump of dark matter, and we see the microwave background behind it or
Yeah.
something has a slight temperature change or something
Yeah,
because it's intervening. So it just doesn't interact
it can
with
only lens it, it can change the trajectory, of
just the
light,
gravitation.
but it cannot block it.
Yeah.
It cannot absorb it. Any other questions?
You need something that has gravity but doesn't block light.
Yeah. And lots of them.
Black hole.
Some people think it's like tiny black holes. That could be-
Yeah, that's sounds like it, doesn't it?
Yeah,
Yeah, but wouldn't those evaporate and emit light?
yeah, because people think they came from like the Big Bang, so there's been enough time for them to evaporate. And back in like I think it was like 10 years ago, people saw these primordial black holes. They would, if you run the calculation, they're supposed to leave an imprint in the cosmic microwave background. And a friend of mine in San Diego thought that he found it, and he was like, "Wow, I'm gonna get the Nobel Prize," and he was wrong. There were some errors in the analysis, and he wrote a book about losing the Nobel Prize.
Hey, buddy, anyway.
But I think, I mean, you said a stupid question. I think there are no stupid questions. I think we just need to, part of the reason I wanted to give you a quiz is for you to exercise the idea that we are all scientists. And everything I discover is usually because I'm asking dumb questions. So it just seems like, huh, this is kind of weird. So it's not so much like eureka moment, but like, what the heck moments that we discovered.
The dark matter be coming from black holes?
So people think that, some people, a small fraction of the community, think that dark matter is really tiny black.
Yeah, I know, you said, that, yeah.
Yeah.
Yeah. But it doesn't come, I guess it couldn't come out. of
In
black
that model.
Yeah,
If I'm remembering correctly, if you talk about primordial black holes, there's been enough time since the Big Bang that basically anything with less mass than say a middling-sized asteroid is already evaporated.
Yeah, and also this imprint on the cosmic background is not there. So that's why I'm not really fond of that theory myself.
Wouldn't you need more resolution to see that imprint anyway?
Maybe. Yeah. Any other questions?
No. No, we're good.
If not, well, thank you so much.
Yes, thank you.
And please stay in touch.